Really exciting session coming up. So it's my pleasure to introduce Warwick McKibbin, who's the Distinguished Professor of Economics and Public Policy at ANU, and has a very, very impressive biography that's in the program. Warwick is going to talk about climate risks in the global economy. Climate risks are clearly really important long-term risk and also short-term and medium-term risk for pension funds and for regulators and supervisors to pay a lot of attention to. And they're very difficult to model, which is why I'm really pleased to have Warwick here to talk about a leading-edge model in this area.
Thanks very much, Mike. I'd like to thank very much IPRA, OECD and IOPS for inviting me to present today. This is totally different to the last session. This is really to bring to your attention current research that's happening across the world, looking at how we think about climate risk in the global economy. It's an active research program with lots of people in lots of places. My main focus in this presentation will be the results or revised results from a study we did in 2021, looking at global economic impacts of climate shocks, climate policy and changes in climate risk assessment. Since doing that work, I've been involved with the NGFS, which is the Network for Greening the Financial System. Some of the regulators in this room are possibly part of that network. It's 137 central banks and financial regulators who are thinking through the issues of climate risk and how that impacts both financial stability, but also the design of monetary frameworks. How should central banks respond when we see the sort of supply shocks that we've seen coming out of the Ukraine war, when you think about the context of climate shocks? And there's a number of papers. I direct you particularly to the NGFS occasional paper, which my team, working with the model you hear about shortly, plus the teams from the integrated assessment models, which I'll describe for you shortly, got together to try and understand each other's approaches and to try and bring the two approaches together. Not completely successfully, but still we learned a lot from each other. There's also a number of papers that the IMF, who have been using this model, have published recently. Chapter 3 of the World Economic Outlook in October 2020, looking at a package of policies at the global level across all countries that could potentially achieve net zero emissions at minimum economic costs. And the fourth one is a chapter that came out in the external sector report, Pandemic, War and Global Imbalances, where we looked at what the climate shocks and climate policies might do to particularly trade flows, capital flows, and also for central bankers, R-star, which is the risk neutral policy rate. So there's a lot of material, and I won't go over it all today. What I will do is talk about climate risk and the global economy. Now, there are four main areas that there's a lot of active research. One is on physical risks, and this is the impact of both chronic climate change over time, as well as extreme risks. And a lot of the work is focused on chronic climate change. This is sea level rise, this is gradual temperature increase, land loss, productivity loss. What we've tried to do in our team is bring in to that extreme events, hurricanes, cyclones, forest fires, floods, and to try and bring in those extreme events to understand better what the long-term and short-term impacts of climate change might be. The second area, which we also focused on most extensively since I've been in this field since 1991, which does seem like a very long time ago, but we've been working on this for many years, including presenting at the OECD several times. And that's the transition risks. That is the policies that will be required to achieve the various climate scenarios that policymakers and negotiators have been talking about at the various COP meetings. These transition risks could be carbon taxes, could be regulation, could be infrastructure, could be a Green New Deal. There's a whole variety of different, fairly substantial policies that will transform the global energy system. So this is not a minor story we're talking about here. If we are going to achieve the net zero, which the scientists tell us is important, we have to change the way we use and produce energy, but also change the way the global economy works, because the entire system needs to adapt, not just the energy system. And so this is a big deal. So we've done a lot of work on transition risk. I won't talk about that today, this is no time, but you can look at our other work. The third area where not much work has been done, certainly not in economics, perhaps in the financial community, that is looking at financial risks. What happens if we've got the wrong view of the future? and people are underpricing the risk in certain types of assets, particularly very large-scale assets which are subject to stranded asset problems if in fact there's either a major climate event or there's a major climate policy in a particular country or a group of countries. And the fourth area, and I will talk about that in this presentation, the fourth area is litigation risks, and I haven't got any lawyers in my team, so we don't touch litigation risks. And there are people, though, worrying about that, and it's becoming a bigger issue. So what I'll focus on today, then, is really the physical risk work we've been doing, the financial risk work. I'm fairly uncomfortable with what we've done to date. It's a very complex issue that we have a set of issues. We can do much better, and we're working out how to do much better, particularly, hopefully, with the NGFS in the new round of short-term scenarios, which they've asked for expressions of interest. So I'll just give you a preview of what I want to talk about. One is that all the various climate scenarios that we analyse, which I'll lay out for you shortly, there are substantial losses to economies over time. And this is highly uncertain. Let me stress, this is highly uncertain. Our strength in economic models is over the next 5 to 10, maybe 20 years, although some people might argue that we have no strengths in using economic models. But in fact, that's our main focus. The work we're doing here is working with the climate modelers who are thinking about the next 50 to 100 years, which is a space in which I don't really understand how we could do that sort of analysis, but somebody has to do it. And until now, it's been mainly the climate modelers and the integrated assessment modelers. We need to bring more economics to it, and you'll see why it's of interest. Firstly, as the various scenarios have higher and higher temperatures, then there's an increase in the economic cost. That's not surprising. There's a lot of adjustments that will occur in the global economy to consumption and investment allocation under the various climate scenarios. And as we've started to look at the financial risk assessment, what happens if markets are mispricing risk, we find that some of those costs, depending on the scenario, can actually be higher than the physical risks in some of the scenarios, which is an important issue. So again, as I mentioned, this is the paper that we wrote originally, but we have updated it substantially. We've used different aggregations from different regions, and I'll mention why we've changed that in a minute. We've done a lot of data revisions, and we've also thought more about how you understand these extreme events. And we've got an incredible amount of data now, looking at very, very, very finite, very finely gridded data from around the world. I should mention Roshen Fernando, who's my PhD student, has just had an internship at the IMF, where he's actually got firm-level data across all countries, all countries where it's available, mostly OECD, but also some emerging countries, and mapped what I'll be talking about here into the impact on balance sheets of individual firms of various climate events historically, and that's pretty exciting research. So let me give you a quick background. What sort of models are being used? Well, there's a set of models called integrated assessment models, and there's three main types of these models. There are models that look at cost-benefit analysis, there are models that focus on the biophysical impacts of climate change, and there are models that are designed for policymakers. There's a lot of difference between these models, but what they basically do in this figure, you can see there's a lot of drivers. There's economic drivers, population drivers, policy drivers. They feed into the energy systems of the globe, the economic systems of the globe, land systems and climate. These are really, really big, complex systems. And they're trying to understand, as you change assumptions on the left, how does the system evolve to give you the outcomes on the right? That is, economic outcomes, emission outcomes, energy pathways, and what happens to land use. This is not something I work on, but it's something that I work with, the teams that do this work. There's also a lot of work being done in the economic space, and that is people running panel regressions with climate variables, GDP and other impacts of different types of climate shocks, structural vector order regression models, dynamic stochastic general equilibrium models, computable general equilibrium models, and agent-based models. So this is a very fertile field. All of these models are very, very different. They give you very, very different insights. I'm not using any of these models. We've got our own model, which is what most of the presentation will be about. Now, what's missing actually in the literature is, firstly, a lot of studies have been focused on chronic risks. These are the gradual increase in temperatures, the gradual increase in disease prevalence. These are things which we think we understand, although again, let me stress the uncertainty is enormous, particularly as you go out through decades. Very few models have so far focused on extreme risks in the economic framework. There's no disaggregation of sectors in many of these studies. And what we try to do is disaggregate from the macro to the micro. In fact, we build up the global economy from individual sectors becoming the macro economy, becoming the global economy. There's also where the sectors do get disaggregated in the CGE type world, they rarely distinguish between physical capital, which is the asset capital used to produce things, and financial capital, which is the assets that are traded across the globe in bond markets, equity markets, foreign exchange markets. Our model explicitly deals with the financial markets, and therefore we have something to say about the financial issues associated with climate risk. And there's lack of a focus on changes in people's risk assessment, and that's again where we're trying to do some new work. So let me just start with how you do this. And again, I wouldn't do this at home. It's very complicated. But there's a literature that goes back to Roshan and Satori. So what you do is you start with a damage function. What is a damage function? Where you look at the historical data and you work at where there's been a climate event, how that event has had an impact on the economy. So for example, Roshan and Satori looked at sea level rise. That just went back. Yes. We look at sea level rise, loss of land as a result of increase in temperatures, changes in crop yields as a function of temperature. So there's a historical data set where you can see what's happened historically. You estimate these damage functions. So you take the climate events, you work out how they've impacted on the economy at the aggregate level by country, and then you use the projected temperature changes from various scenarios about the climate. These are the RCPs, which I'll talk about, representative concentration pathways, different assumptions about how much emissions will be in the atmosphere and therefore what the temperatures will be. So you take the historical relationships, you do the temperature projections and you feed them into those relationships to generate economic shocks in the future, which will then have an impact in an economic model. And most of these shocks end up being sector-specific, either total factor productivity shocks or labour productivity shocks. So that's the approach here. Again, normally done at the aggregate level, so GDP as a function of these climate events. What we do is we go down to the sectoral level, agriculture, energy, mining, etc. The second impact is actually on labour productivity. And on labour productivity, we have heat stress on workers by sector, and we focus mainly on agriculture, manufacturing and the service industries. We also do work on the variation of the incidence of diseases. As temperatures change, there's a large literature on how that's going to impact the various infectious diseases that are out there. Again, you take this historical relationship, you take the scenarios from the temperature, from the climate models, and that gives you labour supply shocks. So we're trying to look at the total factor productivity shocks by sector and labour supply shocks by sector. And again, I won't go through these, but these are the sort of damage functions that people have estimated, Roshan and Satori being the first article in this space. That is, you have the particular economic changes are a function of temperatures. Some of these are highly non-linear, some of these are quite linear. This is one of the big problems that you face in this area, is that the history is maybe looking totally different to the future. And so you've got to make some assumptions about where you think this might deviate from the historical trends, because it's not a continuation of a historical trend that we're facing. In terms of TFP, so we're looking at the damage functions. We've got the historical extreme events, we've got the damage functions for agriculture and energy, and we feed that through a system of relationships external to the model. And the final effect we're trying to look at is, I should mention that, sorry, that was for extreme events. So we're now going beyond the chronic climate change to these increased intensity of extreme events, floods, fires, etc. The final thing that we've brought to the table is looking at how historical events, let's say a hurricane in Florida, has impacted on sectoral rates of return, or in fact the risk premium in different sectors. Now the problem we have again with this is that you can have an extreme event which has had an impact in a small part of an economy, and to find the impact of that in a financial market across the entire economy is a little bit complex. But we've tried to work out the relationship between extreme events historically and changes in risk premium at the sectoral level. Most of the sectoral risk premium show up in relations with firms in agriculture. So that's the sort of the idea, and again, we have damage functions that have been estimated based on the historical relationship. What we're now going to do is take all these historical relationships and impose different scenarios. But before I do that, let me spend 1 minute on the model. This is a very complex model. It has roughly 35,000 equations. It has forward-looking equity markets, forward-looking bond markets, forward-looking firms. Not everybody's rational, but those who use the model make their decisions based on the model, but most agents are using rules of thumb. It's a very complex hybrid of a dynamic stochastic general equilibrium model that you'll see in central banks. They usually about 10 equations, and CGE models, which could have 50,000 equations. We're sort of bridging those two literatures. I should mention G-cubed is currently used at the European Central Bank, the Bank of Canada, the Reserve Bank of Australia. It's widely being adopted because it has this sectoral disaggregation, which enables you to look at relative price shocks, climate issues, which have relative price implications. And basically, you can't do macro without acknowledging the impact of sectors in an economy. And so there's a lot of people now using this. Rio Tinto and BHP use it for their scenario planning work. So it's been widely used. It's been around actually for 30 years. It's just that it's been hiding in the background of climate change, which no one cared about until recently. So what's in the model? Well, let me just mention the model we're now using. Europe is now different. In the original work we did on climate change, Europe, it was all of Europe, including the UK and the Scandinavian countries. Because we've built this model for the European Central Bank, Europe is now defined as members of the Eurozone, and all the rest of the non-Eurozone members are now in the rest of the OECD. So it's got slightly different properties to the earlier work. And this is a disaggregation of a particular sector that's in the model. So we model the primary energy extraction, coal, oil, gas. We have the generation technologies, nuclear, wind, solar, hydro, and others. This passes through the economy to other sectors such as construction, mining, agriculture, durable manufacturing, transportation services. This feeds into a production function where output is made with capital, labour, energy and materials. So it's very standard from a CGE sort of view of the world. So we buy capital, we buy labour, we have energy that's been packaged in different ways in different sectors, we have materials that are packaged in different ways in different sectors, and this gives you a production. Now this substitution is actually estimated econometrically using Dale Jorgensen's data set. So there's a lot of econometrics built into the model, but it's also heavily calibrated because we're talking about a world which doesn't exist yet. So we use as much history as we can, but we have to be adaptable to what we see at the moment in the world economy. So that's the structure of the model. That's also the structure of the consumption decisions of households. They build houses, that's building capital. They supply and purchase labour, and they buy energy and they buy materials. So it's a very, very complex system of all these behaviours, which are actually quite theoretically based on intertemporal macro. So let me talk about what we do then. So this is a graph of the representative concentration pathways. This comes from the integrated assessment models. Each of these pathways is an assumption. So take the bottom, RCP 2.6. That's the assumption that CO2 emissions will gradually peak around now and will gradually come down and hit net zero by 2070. And that implies a temperature by the turn of the century of roughly 0.9 to 2.3 degrees higher than pre-industrial revolution. Now, the first point here is you see lots of lines here. The blue line is the mean from all of the climate models. So there's enormous uncertainty. What we're doing here is we're taking the mean, which is the standard approach in this area. The trouble with the mean is a lot of the most interesting things may come from the tails of a distribution. And this is just telling us the uncertainty in the models, not the uncertainty in reality. And so we're going to start doing some stochastic simulations with different assumptions about what the distribution might look like to get a better idea of the uncertainty. But at the moment we're doing what everybody else does, and we take RCP 2.6 is that emissions profile that you see on the blue line, which generates a temperature profile, and that temperature profile will feed into the damage functions, which will generate shocks to the economic model, and the model will tell us what will happen to various economies and various sectors. So you can see as you move up the RCP scale, you've got more emissions implying more temperature increases. And so if you get up to RCP 8.5, that's probably a world you don't want to see. That has temperatures ranging between 3.2 to 5.4 degrees, relative to the relative to the period 1850 to 1900. We actually don't look at RCP 8.5. We focus on the other three scenarios, but that's what we're using now to drive the shocks to the economic model. And again, some of those outliers are extremely large and cannot be ruled out a priori. So what do we get when we do this? So what I'm showing you now is, so what we do is we run the model out to 2100, and we have a certain set of assumptions about catch-up in technology across sectors to the frontier. We have assumptions from the UN medium-term projections on fertility. We have assumptions about the age earnings profile within each country and how it affects effective labour. So we're trying to do an accurate projection of the future based on what we know today. These projections will be wrong, by the way. You can't project the future, they're just giving us a benchmark. And then we say, now let's take that, we've got no climate feedback at this point. Now let's get the climate feedback from the integrated assessment models, which give us these shocks to productivity, and feed them into that world, and look at the difference between the world without the climate shocks and the world with the climate shocks. And what we're showing you here is the deviation. So you can see the bottom line is, my eyes are not that great, but I think it's probably OPEC. This shows you that by 2100, GDP in OPEC will be roughly 1.3% lower than it otherwise would have been, right? So these are percentage deviations. This graph just shows you that GDP is lower everywhere, but it's widely distributed across countries. So in this case, countries that are highly exposed to the climate shocks tend to have the highest losses. Now, that doesn't look too dramatic because the world economy between now and 2100 is going to be a lot bigger. So these numbers look reasonably small. If you put that in the context of all the scenarios, what I just showed you is the top line. So RCP 2.6, I think we've already missed that. We'll be lucky to hit RCP 4.5, which means the realistic scenarios are the bottom two. And although the numbers are not too easy to see, this is multiples of percents of GDP loss every single year as a result of the climate shocks that we're feeding in. Particularly RCP 6.0, you see that OPEC in particular has very large GDP losses. So when we look at the literature, and again, I'll have to learn to read a screen in long distance without the right glasses on, but you can see that the ballpark numbers are very large and they're consistent across countries. Anyone who's tried to do either the chronic climate shocks or the extreme events, there's one or two new studies on extreme events, these losses are in the tens of trillions of dollars per annum by the end of the century. Now again, very imprecise, very uncertain, but the point is that there's nobody that has positive signs. And it means that there could be a good case to invest in economic activity that can reduce those scenarios to be at the bottom end. What about the sectors? And so we can drill down into particular sectors, and the sector that's most impacted, this is the deviation for agriculture coming from the physical risks. So we haven't put in the transition risks, it's just the physical risks. And you can see once you start looking at agriculture, RCP 2.5, we're getting numbers between 10 and 20% of GDP impacts by the end of the century. Again, the realistic horizon that we should focus on is the first 20 or 30 years because I just don't know how you think about 2100. I always go back when I talk to the integrated assessment models and say, well, what would you guys have said in 1900 about the world today? Ironically, if you're an economist and you run a sort of a GDP forecast and assumed an econometric relationship over the period, you'd actually do pretty well on aggregate, but you get the structure of the world economy completely wrong. But the overall growth rates are fairly much constant. So what about mining? Again, agriculture and mining are the two areas where you get very large losses as you move along the RCP scenarios. Now, ironically, durable manufacturing, and so ideally you would do every sector. Ideally, you would look at these damage functions in every sector. What we've done is we've said, well, which of the sectors that the literature thinks are most affected, and that's agriculture and mining. Let's just do those shocks and see what it implies across all sectors. Interestingly, the durable manufacturing sector, although they aren't having particular shocks except for disease impacts on workers in those sectors, but they're not having the sea level rise effects, they're not having the extreme events in their sector. They still would incur losses because of the spillovers from the other sectors into those sectors. So for example, in a world where there's a lot of climate change, there's a lot less physical investment in the scenario we've developed. If there's a lot less physical investment, then the durable manufacturing sector, which makes the physical capital goods that everyone in the economy buys to produce in the future, will get a negative shock. And so you get these links where if you have a scenario where investment is very weak, then the durable manufacturing sectors will be impacted. And the countries which will be most impacted are those countries that sell durable manufacturing globally, i.e. China and Germany in particular. And so these linkages from the climate to the sectors isn't just the impact on the sector experiencing the climate event, it's the transmission through production networks throughout the world. And so that's the sort of new work that we've done that many others don't do. Now, again, we haven't done the work to see how much the damage functions might impact on these additional sectors, but that is work to be done. And again, this is the service sector. So the only shock coming into the service sector here is the shock to worker productivity coming from increased diseases. Services are very labour intensive, and so we sort of picked that up. Now, the final simulations I'll just talk about is this financial risk. So this is taking the damage functions from the historical experience of extreme events in the risk premium that we've calculated for different sectors. And you can see that the loss of GDP by 2100 is roughly about 1% of GDP, but between 0 and 3% of GDP. So these numbers are reasonably small for RCP 2.6. Again, they get bigger over time. I should stress here, and notice by the way that you do get a jump at the very beginning, because what's happening here is the forward-looking firms and the forward-looking investors understand the new scenario. That is that climate change now has an impact, whereas in the baseline it didn't. And that's going to cause GDP to move instantly, share markets to move instantly. So you can actually, if we focused on that first 5 years, which is swamped by the trend over a decade, but over a century. But if you focus on that, you do get quite a lot of adjustment depending on the scenario you think is about to happen. This could be a very big deal. It's picking up things like stranded assets, coal-fired power stations, etc., and the structural change, which the structural change won't wait until the climate events are getting worse. The structural change is built into people's behaviour at the beginning, and so they'll smooth their adjustment towards this new scenario. And so again, that first scenario, RCP 2.6, when you scale the graphs across scenarios to be the same, you can see that some of these financial risk shocks are actually extremely large. They're getting towards 5% to 10% of GDP loss because of the increased risk in the economy, in production and consumption decisions. Now, this links to a dashboard. So as part of the work we did with the NGFS, all of our results, aggregate, financial, sectoral, macro, global, are all on an online data set that you can download. And in fact, it has been used by the Australian Prudential Regulatory Authority to do stress testing of the Australian financial system for various climate shocks. And so it is available, it's available for free for people to supplement the NGFS scenarios if anybody is interested. So conclusion, what we've tried to do, and this again very preliminary, we're trying to assess the economic impacts of both physical and financial climate risks. We incorporate as many of the extreme events that we've got data on to try and get a better idea of just what the scale of some of these impacts are. We're using damage functions, which there's a lot of problems with using damage functions, but the beauty of this type of framework is you can do different scenarios. So you can incorporate different types of damage functions. You can change the damage functions if you think, in fact, we're underestimating, which undoubtedly we are underestimating these impacts. The reason we're underestimating it is because we're using the averages of climate models and we're sticking them into G-cubed and taking the averages of the shocks. And so this is a real problem with this entire risk literature, is that there's too much averaging going on. And so what we really do need is we need to have a better way of doing stochastic simulations. We don't know what the distributions look like, by the way. I mean, if you assume it's a normal distribution, then all of a sudden you start saying, well, this is the third 100-year climate event in the last 3 years. Well, that's not a normal distribution, right? So we have to have the flexibility to acknowledge the uncertainty and then do a whole range of simulations in this framework so we can get an idea of just how big it might be or how small it might be, and what policy intervention might change in terms of the economic outcomes. Actually, and again, what we're doing here is we're going beyond the NGFS work, which was macroeconomic, to try and get the sectoral impacts. The sectoral impacts really do matter, particularly for economies that have very different sectoral structures than sort of the US economy, for example. All these climate scenarios lead to substantial loss. If you dig into some of the results, like for Russia, you can get some positive effects of temperature change on agriculture coming from the warming of Russia. But on the other hand, when you then exclude the extreme events, you get some very large negative impacts from the extreme events. That's really coming from 3 major droughts that are in the data, which does affect the way we calculate these damage functions. So it's important to stress again that the impacts of climate change are very different across countries. We already know that, but this gives us a better idea of where it's coming from. But it's also very different across sectors. In particular, agricultural intensive economies will experience something very different than service-oriented economies. And what's really interesting, I guess, when you start thinking about these results, is that it's not just where the shock occurs, and that's what happens if you think about partial equilibrium. If you just look at a particular sector in a particular country and forget about the global issue, you can get a very different impact if you take into account all the price movements that occur across markets and all the changes in international trade, international capital flows. So having this sort of interconnectedness in production and in finance actually can quite differently change the results that we get out of just country-specific studies or sector-specific studies. And I think what we've argued, and there's a Brookings discussion paper which sets this out for people, why do you do this? People say to me, why do you do this? And I always say, well, someone has to do it. And if you're going to do it, you might as well have some sort of framework which is historically relevant. It may not be completely appropriate for the future, but you can also see a lot of analysis which is just made up. So you can either rely on the stuff that's just completely fabricated, in which case you have all sorts of bleak end of world scenarios, or infinite progress and mankind discovers all the new technologies, which would be a massive investment boom. One of the key differences between us and the NGFS, which led to a lot of very late night discussions, because I was doing this from Australia and the NGFS being either European or US, the time zone doesn't work. So many late night arguments. But there's 2 things that we found in the scenarios, which is it's documented on their website, and to their credit, they didn't dismiss us from the comparison project. They brought us in as a side project. What was different was 2 things. One was, in the scenarios we did, the GDP losses of the transition policies tended to be quite large. So when you do carbon taxes, all these various other pricing strategies to reduce emissions, in our model, the forward-looking firms see the policies in place, they're credible. So they cut their investment in fossil fuel intensive economies and fossil fuel intensive sectors. Private investment in those sectors contracts. The renewable sectors have the incentive to expand, but we have these adjustment costs in the model which prevent a small sector from getting big very quickly from just a price signal. And so what we find is we get bigger GDP losses at the beginning, which is not really the European view of what will happen in an energy transition. People argue there's going to be all this investment, it's going to lead to a massive boom, and there's going to be an investment boom in Europe. You can generate that scenario in our model, but you need government in there providing infrastructure. You can't just do it by changing the relative price of carbon. And so that's an important insight. We don't know if we're right or wrong, but it changes the debate. The second thing is, I think scenarios are about differences, and in any process where you're trying to get consensus, you're actually going to lose what you learn from a scenario. And so we argue that our model is a reasonable representation of the world that we see. We don't think you can actually have charging stations for EVs next week everywhere in the world. There's going to have to be a rollout, somebody has to pay. And that's another issue in this sort of economic framework versus the engineering framework, is somebody always has to pay. So something has to be invested by somebody. The second issue which we found that's different to the integrated assessment models is, on the one hand, we get more GDP loss at the beginning, but it all goes away in the end. Well, it doesn't go away, but the climate shocks are still there. But what we do get is much lower carbon prices. So we can get a lot more adjustment in the global economy from a particular carbon price, because a carbon price in our world changes everybody's behaviour. It changes the firms that aren't in the energy generation sector. It changes the behaviour of households. They substitute away from fossil fuel intensive goods that become more expensive. So we can get a much bigger emission reduction for a given carbon price than you can in the common scenarios from integrated assessment models. That's still an open debate. I'm willing to believe that we can change that. We can change that in our model if we have bad policies. But if you have optimal pricing, which leads the price to go right throughout the economy, you can get a lot more abatement per dollar or per euro of carbon price. But again, still an open debate, and I encourage you, if you're interested, to look at the NGFS working paper, where we put out on the table our differences, and we discuss the differences, and we point out why that's policy relevant. And that is the website for anyone who's interested in the G-Cube model and any of the associated papers. And I will stop there. I think I'm on time.
Thank you very much. You are indeed on time, and we have plenty of time for questions. I mean, I'd summarize some of the messages to be that in addition to worrying about the trend, there's a lot of uncertainty. And for the pension regulators and insurance supervisors in the room that have to think about the uncertainty and scenarios in doing their setting rules and looking at firms and looking at pension funds, it's a big problem. And it's not just climate that's a big transition in the next 10 or 15 years. There are simultaneously big transitions in demography and in technology with AI and robotics, and they interact. I mean, people that are older don't move around as much, so migration's harder. The technology for climate change and climate mitigation is still under development. And so there are just a lot of things that are interacting in very complex ways. And models are very valuable because they highlight the degree of uncertainty, and they can highlight the ways things can go wrong. And it's just very helpful to have the understanding that comes from state-of-the-art models. So just a big thank you.